So now I would like to discuss about actual vapor compression cycle. So now I will discuss actual vapor compression cycle. So generally in actual vapor compression cycle, we are superheating the working substance after evaporator so that this working substance which is going into the compressor is not having any vapors. Similarly, we are using subcooling after coming working substance from the condenser, and due to this subcooling we are having a good quality of working substance after expansion through throttle valve or capillary tube. So these two things is calling superheating and subcooling. So now let's draw the pH diagram for understanding the superheat and subcooling in a vapor compression cycle. So now for actual vapor compression cycle, as we discussed, superheating and subcooling is incorporated in ideal vapor compression cycle. So I am just trying to draw these two things. This one is pH diagram, and in pH diagram this one is the dome shape here, and now I will show the processes here. In that process here, first of all I will draw the actual process here. So I will show all these things here, then it will be very clear. Suppose in actual, this is dotted line, we are at saturated vapor state here, that is point suppose 1 dash, and we are going up to 2 dash, and from 2 dash to 3 dash we are here, and we are coming to 4 dash. This process is without subcooling and superheating, but in case of superheating, what will happen? This one is the working substance leaving the evaporator and entering into the compressor, but we are superheating it. So the state will come here. So this one, the state will come here. This one is 1. And now from 1 to 2, we are having isentropic compression, that is 1 to 2. And similarly, 2 to 3 dash, we are in condenser. So again we are going for subcooling, then again we will decrease the temperature here. We are here at the stage 3, and then we will go for expansion, and now we are coming at the stage 4. So this one is the difference between the vapor compression cycle without superheating and subcooling and with superheating and subcooling. If you see this thing, this one is nothing but degree of superheating. So we are calling it degree of superheat. And this one, that is 3 dash to 3, we are calling it degree of subcooling. So now it is clear, in actual vapor compression cycle we are implementing superheating and subcooling. So why we are implementing superheating and subcooling, we have already discussed, but here I will write for our better understanding. So in order to ascertain that that there is no droplet of liquid refrigerant being carried over into the compressor. Some superheating of vapor, some superheating of vapor, some superheating of vapor is recommended. Some superheating of vapor is recommended after the evaporator. after the evaporating. So now it's clear why we are going for superheating. Similarly, we will talk about subcooling. A small degree of subcooling of the of the liquid refrigerant after the condenser as shown in figure is also also used to reduce also used to reduce the mass of vapor formed during expansion formed during expansion means we can say that the quality of the working substance is increasing after expansion so that too many vapor bubbles do not do not impede do not impede the flow of the flow of liquid refrigerant through the through the expansion wall. So now it's clear why we are going for superheating and subcooling. So the main important point I am writing here, due to the superheating and subcooling, both will contribute in increasing the refrigerating effect. So I can write both the superheating and subcooling contribute contribute to to an increase in refrigerating effect. So both are contributing in increasing the refrigerating effect. So now I will discuss about a very important formula, that is volumetric efficiency. So now we will talk about volumetric efficiency. Volumetric efficiency. So the volumetric efficiency is generally used for compressor in case of refrigerator. So now volumetric efficiency, I can write the formula for that. That is nothing but ratio of actual volume of gas drawn at evaporator pressure and temperature. Gas drawn at evaporator pressure and temperature. To the piston displacement. So mathematically, I have already written the volumetric efficiency is nothing but actual volume of gas drawn at evaporator pressure and temperature by piston displacement. So now the volume of gas handled by the compressor is also given by one formula. I am writing here. Volume of gas handled by the compressor equals to W into V1, that will be in meter cube per second, or another formula is pi by 4 d square L n by 60 into n into and volumetric, eta volumetric. So here W is refrigerant flow rate, refrigerant flow rate, flow rate. Small v1 is the specific volume of the refrigerant at the compressor inlet, D and L are the diameter and stroke of the compressor, stroke of the compressor. N is the number of cylinders in the compressor, and N is the RPM. So by using this formula, we can easily calculate volume of the gas handled by the compressor. Sometimes uh, we are using the clearance. So the one more formula for volumetric efficiency we can write here. Eta volumetric equals to 1 plus C minus C P2 by P1 to the power 1 by N, where C is the clearance. So now the one more formula for volumetric efficiency is 1 plus C minus C P2 by P1 to the power 1 minus 1 by N, where C is the clearance. Now I will talk about the various kinds of refrigerant. Means in daily life we are hearing the refrigerant is R12, R132. So what will be the chemical formula for R12 and R132? So there are various kinds of refrigerant which are denoted by R with some numbers. So what is the significance of this number, and by this number how we can achieve the chemical formula? So just I am writing some theory regarding refrigerant and how we can get the correct chemical formula by the number represented by this refrigerant. So now let's talk about refrigerants. So the most widely used refrigerants, the most widely used refrigerants, refrigerants nowadays are a group of halogenated hydrocarbon, halogenated hydrocarbon, hydrocarbons marked under the various marked under the various marked under the various marked under the various proprietary name of various proprietary names of freon, zenitron, arcton, isotron, etc. Then there are either methane based or ethane based. These are either methane based or ethane based or ethane based where where hydrogen atom hydrogen atom are replaced by chlorine and fluorine atoms. Hydrogen atoms are replaced by chlorine and fluorine atoms. Fluorine and fluorine atoms. Fluorine atoms. So this things is very important. Here the refrigerants are either methane based or ethane based, and in that refrigerant the hydrogen atoms are replaced by the chlorine and fluorine atoms. So the methane based methane based compounds are denoted by a number of two digits number of two digits where the first digit minus 1 is the number of hydrogen atom is the number of hydrogen atoms, and the second digit indicates the number of fluorine atoms indicates the number of fluorine atoms while the other atoms are chlorine while the other atoms are chlorine. So here it is very clear in methane based compounds that is denoted by two digit number, and the first digit minus 1 is the number of hydrogen atom, and the second digit indicates the number of fluorine atoms while the other atoms are chlorine. So let's take an example. For example, we are having R12. So now R12 is a two digit number, it means it's a methane based compound. So the first digit minus 1 will be the number of hydrogen atom. So I will write number of hydrogen atom equals to first digit minus 1. So the first digit here is 1. So 1 minus 1 will be 0. So number of hydrogen atoms will be 0. So now the number of fluorine atoms. So number of fluorine atoms here will be second digit. Second digit will show the number of fluorine atoms. So second digit here is 2. So 2. So number of fluorine atoms will be 2. So now I can write the other number, then while the other numbers are chlorine. So the number of fluorine atoms. Here the two hydrogen atoms is replaced by two fluorine atoms, and hydrogen atoms are 0. Means in methane base there are 4 hydrogen atoms. So 2 replaced by fluorine, there is no hydrogen atom. So remaining 2 will be replaced by fluorine. So the number of fluorine atoms will be 2. So now I can write the chemical formula for that. So the chemical formula will be CCl2F2. Number of fluorine atoms is 2. There is no hydrogen atom. So this one is the chemical formula for R12. Now let's talk about ethane based compounds. So I am writing ethane based compounds are denoted by a three-digit number by a three-digit number where the first digit is always 1. Where the first digit is always 1. The second digit minus 1 is the number of hydrogen atom. The second digit minus 1 is the number of is the number of hydrogen atom and and the third digit indicates the number of fluorine atoms, and the third digit indicates the number of fluorine atoms and and other atoms in the hydrocarbon being fluorine, and the other atoms in the hydrocarbon being fluorine. So now it's very clear. In ethane based compounds, it is generally denoted by a three-digit number in which the first digit is always 1 and the second digit minus 1 gives the number of hydrogen atom, and the third digit indicates the number of fluorine atoms, and the remaining atoms will be the chlorine atoms. So let's take one example here. I am taking an example of R113. So I am taking example here. Example R113. So here we are interested in chemical formula for R113. So it's a three-digit number. So obviously it's a ethane-based compound. So the number of hydrogen atom according to theory, the second digit minus 1. So the second digit minus 1. So the second digit here is 1. So 1 minus 1, it will be 0. Now number of fluorine atoms. So the number of fluorine atoms here will be third digit. Third digit is the number of fluorine atoms. So third digit here is 3. So number of fluorine atoms will be 3. So now come to the number of chlorine atoms. So according to the theory, the remaining atoms will be the chlorine atoms. So now if you talk about ethane base, that is C2H6. So here the total number of hydrogen is 6 and it can be replaced by other atoms. But here the number of hydrogen atoms are 0, means all the 6 is replaced by either fluorine or chlorine. So fluorine is already replaced 3. So the remaining 3 will be replaced by the chlorine atom. So the number of remaining atoms will be fluorine atoms. So now we can easily write the chemical formula for R113. So the chemical formula will be here C2, that is for ethane, and in place of H6 we are having no hydrogen atom, so hydrogen will be 0. Fluorine atoms is 3, so Cl3, and fluorine is 3, so F3. So this one will be the chemical formula for R113, C2Cl3F3. So remember these things are very important and sometimes it may ask in GATE examination. So now I will discuss about the air cycle refrigeration, or we can say that gas cycle refrigeration. So now let's talk about air, or we can say that gas cycle refrigeration. So here remember one thing, in most commonly cycle which is based on a vapor compression cycle, and the COP of vapor compression cycle is more. But sometimes we have to use air as a refrigerant, like in aircrafts, because in aircrafts on the height the air is present in a large quantity. So this air we can use for the refrigeration, but in that case the COP will be less. But still we are using this air for a refrigerant in air cycle refrigeration in aircrafts, because the air is widely available at the height. So this kind of cycle basically used in aircraft. So first I will draw the cycle, and then we will talk about in terms of COP. So now let's draw the block diagram for air cycle refrigeration. So similarly, air cycle refrigeration, we are having a cooler here. So this one is cooler. The component will be same, but there will be a major difference I will tell later. And here we are having a compressor. Here we are having refrigerator, or we can say that evaporator. So I will tell it's a evaporator. And here we are having expander. So if you remember, this thing means in vapor compression cycle either we are using capillary tube or throttle valve, but here I am using expander. So I will tell later why we are using expander in air cycle refrigeration. So this one is expander, here evaporator, this one is condenser, and this one is compressor. So here I am marking the states, that is 1, that is 2, here that is 3, here that is 4. So now let's draw this thing on TS diagram. Here TS diagram. So here I am having this dome, but we are away from this dome, because especially in air cycle refrigeration, the phase of the working substance is not changing. So we are dealing with the refrigerant in that region. So we are dealing with the refrigerant in that region. So now I will draw the process 1 to 2. I am drawing, that is isentropic compression. It's 1 to 2. 2 to 3, that is constant pressure heat rejection. 2 to 3, that is 2 to 3. Now 3 to 4, that is the expansion in expander, that is 3 to 4. And again 4 to 1 is constant pressure heat addition. So this one is a typical process for the air cycle refrigeration. And if you see this process, it's looking like a Breton in a reverse direction. So it's nothing but reverse Breton cycle. So I can say it's nothing but reverse Breton cycle. Breton cycle. So we can say that the reverse Breton cycle is the cycle for air refrigeration. And now I will say why we are using this expander. So now let's write some things for this expander. Here expander replaces the throttle valve, throttle valve of a vapor compression system, of a vapor compression system. So as I already discussed, like in vapor compression system we are using throttle valve or capillary tube, but here in air cycle we are using expander. The reason is because the drop in temperature, because the drop in temperature, drop in temperature by throttling a real gas, by throttling a real gas or air, throttling a real gas or air is very small, is very small. That is the reason why we are using expander, because in total walls the drop in temperature of the real gas or air will be very less. So we have to use expander for achieving the higher drop in temperature. So that is the reason why we are using expander in place of capillary tube or total wall. Now we have already discussed it is nothing but a reverse breakdown cycle. So now I can easily write the COP. So the COP of reverse breakdown cycle, reverse breakdown cycle, or we can say that air refrigeration cycle, air refrigeration cycle is given by COP equals to 1 by P1 by P2 to the power gamma minus 1 by gamma minus 1. COP is given by 1 upon P1 by P2 to the power gamma minus 1 by gamma minus 1, where P1 is pressure after compression, pressure after compression, after compression. So here after compression means on this diagram this one is P1 and similarly this one is P2, that is before compression. So P1 is the pressure after compression, similarly P2 is pressure before compression, pressure before compression, before compression. So this one all about the air cycle refrigeration, and now I think the theory part regarding the refrigeration cycle is sufficient. So in the next lecture we will discuss about the problems and we will see how we can solve problems easily.